expensive because you're both reading and writing. Yeah.
So why aren't we just, maybe I missed it because I came in a little bit late, but why aren't we just storing the pointers at the before the allocated block?
So there are various reasons, but you can just think that if you store it there, then maybe the way the attacker gets to you is from the previous block, you know, to the beginning. So one way or the other, the attacker can overflow. So is this clear? Right? So you have this, which is to delete yourself from the queue, from the W linked list. You're just going to set, you know, go to your back and then set the forward to go here. Right? So that is what this is. If the attacker controls both these values, then this is equivalent to A arrow forward, which is the same thing as star of A plus some offset. Okay? Maybe, you know, some constant offset that you know ahead of time equals B. So by controlling A and B, the attacker can write an arbitrary value at an arbitrary location. Anything else? Yeah.
Professor, I have a question from the slides and not from the question paper.
Yeah.
For the SFI, the software fault
Yeah.
isolation, for when we apply the same thing to CISC architectures, we have mentioned like there are two kinds of difficulties. One is variable length instructions, and the other is insufficient registers.
Yeah.
In insufficient registers, we have mentioned like PIT-S field. So I'm having a hard time understanding the significance of this PIT-S field, like what exactly is it doing, and you know.
So PIT-S field is the name of the particular solution we talked about. Okay, so the people who built that system gave it a name called PIT-S field. Now, it happens to be a small town somewhere close to Boston. The work was done at MIT, and they wanted to have a system name that had SFI in it, and they found a town name that had SFI in the middle, and so they called it Pittsfield.
But this is not doing anything with the problem. I mean, it's mentioned inside the problem too, like insufficient registers, and it's saying like it uses EBX as a dedicated.
1 second, right? So let me. Okay, so what is it?
So I mean, the property which exactly it is implementing inside it, like it uses EBX as dedicated registers, and so extra adds. I wanted to understand like. Does it apply to all the CISC architectures? Like, what exactly this is?
This is SFI for x86, right? And anyway, I'm not sure. Are there other CISC architectures that are in existence? I'm not sure, right? So it's somewhat questionable whether ARM is really, RISC. But other than that, when we say CISC, it pretty much means x86. But is that the only question you have?
I needed to understand like what exactly means when it says like it takes EBX as a dedicated register and treats ESP and EBP as sandbox registers. So
okay, so what that means is, okay, dedicated register, we have already discussed what a dedicated register is. It's something that the program itself is not able to use, and it is only used by the SFI checking code, right? nobody else can, load or store or modify or use EBX register. Okay. Now, what is a sandbox register? A sandbox register, what they mean here is that its value is always in the range that you expect. So once again, what it means is that the program is not free to use these registers in whatever way it chooses, but instead the ESP and EBP are used only for referring to the stack and referring to the base of the stack frame and so on, and only instructions that change the stack frame or push things onto the stack and so on, those are the only ones that can change these registers. So you don't have to worry about the possibility that the attacker has changed the, so for instance, if you think about a ROP attack, right? Typically a ROP attack, for a ROP attack to work, the attacker will typically change the ESP to point to some region of memory that they have already controlled, right? So they have already written something into memory, and they want to set the ESP to point to that memory, because from then on they can fully control the ROP payload. Okay? So that means in order for that attack to work, the attacker has to corrupt ESP, right? And what this is saying is that no such corruption of ESP or EBP is possible. Yeah.
How's it sandbox then? How do they know it's changed?
So, basically, remember that for SFI, you still have the compiler. It's a compiler that generates the code, right? So therefore, it's easy to ensure when it is generated that ESP is modified only in certain ways, right? And so at the receiving end, they do have to check whether the stack modifications are permitted or not, okay? And the way this will be fixed is, their verification should succeed, right? So for instance, if let's say there is an alloca in the function, which means that it would not be possible for you to verify whether the stack is reset properly at the end of the function, right? Because if you push, right, you can immediately tell how much the stack pointer changes. But if you do an alloca, then the argument to alloca can be a runtime generated value. Therefore, you won't know statically what is the size of the stack change. So they will expect that there will be code at the end of that function which either resets ESP to EBP, right? And in that case, because EBP is reliable, ESP will have a trustworthy value. Or anytime you have this kind of code that modifies the stack by some unknown value, there will have to be a check that no, I think this is what I said before is the only way. If you have an alloca, then they will expect that the ESP will be loaded from EBP at the end of the function, and that's how they will verify. And any sort of uncheckable use of ESP or EBP will cause the program to fail the check, and you'll say, oh, this is bad code, I'm not going to run it. Anything else? Yeah?
As for the problem set 1, the 9th question has no solutions given to it. Do you mind discussing that particular problem?
Which problem?
9th one.
solution is there. It's all marked in the program, right?
Oh, sorry, I didn't go through it. My bad.
Yeah. So yeah, so the answers are there, except maybe for part D, which says, you know, if you have full metadata maintenance and checking at runtime, well, the answer, you know, if you do that, then you will detect all the errors and you won't have any spurious errors. So that's, whereas some of the other techniques which try to speed up the check or maintain less metadata, they may have both you know, false positives and well, okay, I shouldn't say that. Some techniques will have false positives, in which means you report an error when there is a delay, and some techniques will have false negatives, which is to say that there is an error that goes undetected. Okay, and then you but if you do the full metadata maintenance, then neither is possible. Yeah.
Same problem, there is a line that says you can assume that the variables are allocated in the order which
Yeah.
they are declared,
Yeah.
and R42 will access Q. Shouldn't that be operated?
Yeah, okay, yeah.
Yeah, so R42 would be not pointing to Q because Q is declared. So R is declared first and Q is below it. So R42 would be near the EBP and not near Q.
Okay, so when I say declared in the order, well, anyway, so you know that there is only one interpretation that is consistent with that statement, right?
Yeah.
So take the interpretation that's consistent with the statement that R42 will refer to Q. Anything else? It's late, it's getting dark, so. Okay, very good. Good luck.